Hello, good afternoon. Um, can someone respond so they can hear me? If they can hear me, yes?
We
We
can
can
hear
hear
you.
you.
Great, okay. So here we are, week 9. We're going to start digital electronics. This week, we're going to have two lectures today and Wednesday, and then you'll do an experiment on this week. And then you'll also, there'll be one lecture next week on Wednesday, pulsed ICs, and then you'll do another experiment next week, and then there's only one lab report due for these 2 weeks. That's why I've called the labs 8A and 8B down here. And then we're going to have a final exam. Let's see, not a week from Wednesday, but 2 weeks from Wednesday on magnetoelectronics, optoelectronics, and then digital. And that's the last exam we'll have. We're not going to have a final exam. We're going to have a final project instead. And we'll talk about that a little later. Any questions on some of this information here? Okay, digital basics. We'll go over that first. These are the basics of all our computers now. I mean, everybody's talked about quantum computers, but we're quite a ways away from that right now. So we'll go into a Boolean algebra, truth tables, theorems a little bit, then we'll look at logic gates because that's what we're going to be using in our experiments. Basically the or and not NAND gates. Then we'll look at some adders. These 2 lectures, Monday and Wednesday, are relatively short. They're not the full hour and 40 minutes, and I'm sure you'll be glad about that. Okay. What is digital? Digital, you either have something like a 1, or you have nothing like a 0. Or you can also call that true and false. And why digital? We'll talk about that. How to do math. We saw that we can sum voltages in analog, but that's not very precise. With digital, we can determine whether there's something there or not there fairly easily, and that's the basis of it, basically. I'll go just a tiny bit into the history of computers because I always find the history interesting. And then we'll look at these logic gates and the adders. Okay, computers. The history of computing goes back many thousands of years. So, I mean, not just the number system, but how do what was it addition? What was multiplication back then? Well, when you had huge construction projects like the pyramids, there were accountants and engineers that had to use math, and they had to multiply and add and so on. Then along came the Renaissance, and people thought of a mechanical calculator, and Babbage designed a difference engine, they called it, in the 1800s, but it had gears, but it would tabulate polynomials. Well, the problem in constructing something like this, you can imagine that the materials and the machining wasn't that good to have something like this, something as complicated like this, running that many gears and so on, last very long. So he passed away before they actually made a working version of it. And then came the 1900s, the Turing machine, Alan Turing. There's a movie called The Imitation Game. and I think he and von Neumann, you associate with the beginning of digital computers. He considered, Turing considered a hypothetical device, and he came up with the idea of algorithm, that you have some input and you want some output, and then you have a set of instructions that that leads you from, generating an output from the input. He had a very interesting paper in 1950, the Turing test. Let me see if I can get this new share here. Okay, can you see this paper? It's a quarterly review called Mind, about psychology and philosophy. And the first part of his paper was called The Imitation Game. And the whole idea was, can machines think? Okay. And we know we can generate numbers and things from computers, but can they think? So he went through this whole philosophical discussion about can machines think? And there's a lot of text here. I hadn't read it in some time, but I glanced over it again this morning. Let's see if I can find some things. Anyway, there were objections about, theological objections, other things like that, mathematical objections. Can a machine think? Well, maybe we're getting a little closer to it. One thing I was trying to find was, I guess it's near the end here. Excuse me for scrolling down all this. I captured all the text and put it in a Word file. Well, at some point, he said, in 50 years, we'll be able to store 10 to the 9th pieces of information, and that would be the year 2000. And yes, we can store a gigabyte of information. So he was right on, 50 years ahead of his time. I can't quite find it right now, but so can computers think? Well, we have AI, we have artificial intelligence, and one of the ways to look at that, a very oversimplified way to look at it, that is that the information that comes in hasn't a fixed algorithm, that the algorithm can change as it analyzes the input. Okay, so maybe someday some machines will be able to write amazing poetry and music and things like that. People have been working on that for years and years. Anyway, I just wanted to show you that because I thought it was interesting. So let's go back to here. Can machines think? Perhaps in your lifetime we'll get close to that. And then along came the electrical computer. I mean, some of these the old computers in the early part of the 1900s, the early middle parts of the 1900s, they had relays in them, and then they went to vacuum tubes. And they used to have a vacuum tube computer at the Children's Museum in Boston, and it was interesting. It looked a little bit like this. They had parts of it, and then, but it was a little more modern than this, and it had all these bays that you'd plug in these boxes, and there were holes near each one of the boxes, And I asked somebody what the hole was for, and he said, well, if it gets too hot and catches on fire, you could put the fire extinguisher up to the hole and, and blow in and put out the fire. Anyway, vacuum tubes get hot, but then semiconductors came along, and then you could make things really small. And then on top of that, integrated circuits where you could put a whole lot of semiconductor devices together. That really enhanced computers quite a bit. And here's the first PC computer around 1970. And then, you know, people are working on, they're making quantum computers now, and there's a lot of work by IBM and Google and other companies, and everybody's saying, I have the best computer by my measurement, and the other one says, well, I have the best computer by my measurement. Anyway, they can't do a whole lot with it now. In fact, the only algorithms that I'm familiar with is factoring numbers and sorting numbers, but it'll certainly be good for encryption, certainly for that. Okay, let's take a look at our number system. Well, you know, we've all counted on our fingers, right? Our 10 fingers, and I can see I spelled fingers, misspelled fingers there. The Egyptians needed some number system 5,000 years ago, and it was base 10, as I understand. Chinese had something 3,000 years ago. Then the Romans came up with Roman numerals, where they used letters and you can see those still on buildings now, where if a building was built 100 years ago or so, that you know, they'll use Roman numerals to represent when it was made. And then zero. People started needing zero in mathematical equations. Okay, but anyway, we come to binary, base 2. And that's really hard to deal with if you just have zeros and ones only. So you combine a number of binary numbers into an octal number, 8 bits, which we call a byte. And then even a little farther than that, 2 bytes in a hexadecimal number. So that's another numbering system, but these are based on binary. Okay, the binary system. If we had a base 10 system, the digit on the right-hand side, which we call the least significant bit, would be the ones column, then the tens and the hundreds and the thousands. Well, the binary system has 1s, 2s, 4s, 8s, 16s, and so on. So it's a factor of 2 going to the left on each one instead of 10 as in a base 10 system. So 15 in the base 10 system would be 8, 4, 2, and 1. So you'd have to write that as 0, 1, 1, 1, 1. This is 1, this is 2, this is 4, this is 8. You sum those together and get 15 base 10. And here's the numbers up to 8. And the byte became fairly important early in computers. That instead of having just numbers like these, you could put them together in bytes. And a byte is 256 numbers because it's 8 bits. And a number I remember that's fairly handy sometimes for calculations is 2 to the 10th is 1024. So you can use 2 to the 10th is equal to 1,000. So that's a round number that you can use for some back of the envelope calculations. Then there's something called ASCII code, and each keyboard character, when they first started making keyboards, each keyboard character was designed an ASCII code, and that code was just one number, one number in a byte. So it had 256 256 keystrokes, basically, or possible things you could have on your keyboard. Any questions on some of those things right now? Okay, so now that we have a numbering system that we're going to use in computers, how do we use it? So how do we do the algebra, Boolean algebra? So you represent Boolean numbers, say A and B. A can be a 1 or a 0, B can be a 1 or a 0, and you define operations. Just like you would in math, you have addition, multiplication. The addition sign means or, and the multiplication sign means and. Sometimes you can leave out the dot here and just say AB means you're going to and those two numbers. And then you have a not, which if A is 0, then not A is 1, and the opposite. So you can have or, and, or not functions. So those are operators. So here's a truth table. I think some of you have probably seen this in some classes already, but I suspect a lot of you haven't. So if you have inputs, say A 0 0 1 1, B 0 1 0 1. So we just write all the possibilities. You have 2 zeros, 2 ones. A or B can be 1 right here. So an OR function represented by a plus sign would say if any of these, if any of A or B are 1, then A plus B is going to be a 1. Okay. An and, which is like multiplication, says you have to have both A and B equal to 1 before you can get a 1. Otherwise, you get a 0. And of course, a not is just the opposite of A. Not A is just the opposite of A. Okay, and you have some theorems. I won't spend much time on this, but you have some theorems. You have some operational properties of these operators that you can commute. That is, it doesn't matter if you use A first and then B, or B and then A. This works for both plus and times, or and and, or and. So that works whether you do one first or the other, doesn't matter. Associative, if you have only ors, the pluses, then you can associate. You can do the A and B math first and then do C, or you could do the B and C math first and then do A. And as long as you have all ors with pluses, or all times with ands, you can do that. But if it doesn't necessarily work if you have both or and the ands in a formula like this. Then you have distributive properties that you could do A and B, find out what number that is, times C, or and it was C, or you could and A and B, and then you could and B and C separately, and then you could OR the two afterwards. So that's a distributive property. And this is important, that you have these three functions here, or, and, not, but De Morgan's laws says you only need two of these, a not and an or a not and an and. And we'll get to how you can take some of these operations and combine them to make other operations. And this is one example where only need 2 of them. Let's take a look at this.
In this lesson, we're going to discuss logic gates and how they apply to digital electronics. We're going to talk about the 3 basic logic gates, the AND gate, the OR gate, and the NOT gate. We're going to construct some truth tables for these logic circuits so you can see how inputs and outputs relate to each other. We're going to use these truth tables to provide Boolean theorems and prove that they're actually accurate. And we're going to express the outputs of logic circuits using Boolean expressions and vice versa, Boolean expressions as logic circuits. So let's get started. First thing you want to remember is the OR gate is represented with a plus sign. So when we write out the Boolean expression, if we have A or B, it's going to be A plus B. So anytime you see a plus sign in Boolean expressions, that means OR. AND is represented by multiplication, and you can see it as an asterisk or dot, or sometimes they're just 2 terms stuck together.
Let's see. Yeah, I just wanted to show you that to start with. I didn't want to play the whole thing. It's quite long. Okay. Any questions so far? So we'll get to see how to use this. Okay, so in electronics, we have actual gates that do these logic operations. That is, you put voltages into them and you get a voltage out. So logic gates have wires like A and B going in and some output. And we're going to be using basically 0 and 5 volts. I mean, there are other schemes like your computer. They're always trying to make computers and your phone use less power, right? Because you don't want, like your phone, you don't want to charge it very often. So computers and your phone use often lower voltages than 5 volts, but 5 volts is kind of a standard that they set quite a while ago. Okay, so here's an OR gate, 2 inputs. It has a curved back and a pointed front. An AND gate is represented by this D-shaped object here, and a NOT, it just has 1 input and 1 output, and it NOT, and there's it's a triangle, but the circle is the important part. When you put a circle on something, it means NOT. You're just inverting whatever the 1 was or the 0 was. Shout if you've ever used Minecraft. Anybody?
Yes.
Of course.
Yeah. My son, who's he's just a few years older than you are, he used that quite a bit. Let's take a look at logic gates in Minecraft. Share.
Hey guys, this is Andrew from the Minecraft tutorial, and today we're going to be talking about logic gates.
There we go.
Hey guys, this is Andrew from the Minecraft tutorial, and today we're going to be talking about logic gates. This is advanced redstone stuff, so if you don't know the basics, make sure to check out my basic redstone technique. But yeah, so the first one we've already seen before. It's an inverter or a NOT gate. So when it receives power, it changes what state the power is in. So it's not receiving power right now, so it'll output power. If it is receiving power, it will output no power. So So the door's open with no power. When we give it power, the door closes. Next up is an AND gate. The AND gate is basically what it does is you have to have the left lever and the right lever. So, for example, just using the left lever will not open the door. Just using the right lever will not open up the door. You actually have to have both of them down for the door to open. This can be really useful, and I'll show you how a little bit later. Next up is the OR gate. With the OR gate, both switches will open up the door. So this switch or this switch will open up the door. And even when they're both down, it'll stay open. Now this is really, really awesome. It's a T flip-flop.
Okay, we won't go into T flip-flops now. That's a little later. So when I gave this lecture 7 years ago, one of the students, he called himself "that weird physicist," put something into Reddit, and it got 175,000 views. And people wrote in about Andrew, and they'd say, "Andrew, you can call yourself professor now on, doctor, professor, MD, PhD." And Andrew says, "Wow, I never thought my video would be used at a university." So he was really he was very happy about that. And then I put this up in a this slide later, I think a year later, a couple years later, and that got 200,000 views. Okay, so that really made his day, that he's he had something to do with educating students in universities. Okay, logic gates. Let's take a look at additional operations.
Professor, I have a quick question.
Sure, yeah.
Will we be allowed to use Minecraft for a final project?
We haven't quite worked that out yet, because normally the project was everyone would pick a project. It'd be a project that would have to couldn't be too sophisticated. You had to be able to do it in 2 weeks, or 2 lab sessions. But since most of the people are not coming into the lab, we can't do that hands-on. But that is a possibility. So send us an email suggesting that. Okay. Yeah. I mean, preferably something that you haven't done already. I mean, people have made computers, 32-bit computers in Minecraft already. Okay, so you can do additional NOT operations. So here we have an AND here, and if we put a small circle on it, then you take whatever output the AND gets and you NOT it, and that's a NAND. So I put a bar underneath it because it wasn't that easy to put the bar on top of it, but just means you're taking A and B and then NOTing it. Okay, so and you only get a 1 if both A and B are 1s. Then when you NOT your 1, you get a 0. When you NOT the 0s, you get 1s. Okay, the NAND is the most important gate. In fact, that's probably more than 99.9% of all gates in the world are NAND, and a lot of memory is built on that too. Not just for computation, but also for memory. Okay, the second one is you can take the OR, and you can put a NOT on it, and you make a NOR, a NOT OR. Okay, so that just takes a 0, makes it a 1, takes the 1s, make it a 0, and you get a NOR chip. I mean, so you can buy these things, ANDs, NORs, ORs, you know, and so on. Now there's one more thing. So you can add the NOT to something. You can also do something making a gate exclusive. Okay, so you know that OR means if either A or B is 1, then you get a 1. But if both A and B are 1, you also get a 1. So that's what. So then, if you make an exclusive OR, that says do everything here except when you have both A and B 1, then make that a 0. Okay, so that's an exclusive OR. You're excluding when both A and B are 1. Just excluding that. And then you can make an exclusive NOR, which is just changing the, you're just putting a NOT, you just put a NOT on the, put a small circle on the XOR. You put the curve in the back, the extra line in the back for exclusive, and then you put a small circle in the front to be XNOR. Any questions so far? Okay, inside logic gates. So what we use is what's called transistor logic. And that's basically just using 0 and 5 volts. We call it TTL for short. TTL, transistor logic. That's one of the earliest standards, and it's the one for most of the chips that you'll see. We're using chips in the 7400 family of digital integrated circuit gates. How do they work? Well, does this look familiar? It should, from the transistor experiment that everybody worked on. So this is called a common emitter, right? Emitter has the arrow on it, and it's tied to common here. If you put 5 volts on here, it turns the transistor on, and this resistance goes to near 0. So it pulls this voltage down to 0. So you put a 1 in here, and you get a 0 out here. So this is a NOT gate. And you can do similar things with an OR gate, just using two transistors here. If either one of them goes on, then you get some output. Okay, so you can treat transistors just as on and off switches. And we're not really cared about how much gain we have. We're just interested in whether it turns on, transistors turning on or turning off. That's all we're interested in. Here's inside of a NAND gate. Well, here's actually a NAND gate here. But you have 2 transistors, so you have 2 inputs here, and they're in series. So if either one of these is, so you have to have both of these on for this thing to go to 0, this voltage to go to 0. So you have to have 5 volts here and 5 volts here to get this to go to 0. And this is with transistors, and this is with FET, field effect transistors. It's basically the same as this is here. We call it a MOSFET. Okay, so that's what's inside. That's what's inside of these things. But you can see how electronics is built on some of the things that we've worked on so far. You know, this original transistor circuit. And how many times have we seen voltage dividers, right? Resistor here, and here's resistors here, basically. Voltage dividers. The NAND gate. Okay, you can. One of the powerful things is that with NANDs, that it's easy to create other gates. A NAND is such that any 0 gives a 1. That's a general rule. So if you take a NAND gate and you tie the A and the B input together, it just gives you a NOT gate. And if you want an AND gate, you just take two NANDs, you take a 2-input NAND, and then you tie the inputs here, which is just a, so this is a NAND and this is a NOT. So effectively what this looks like is it looks like a NOT with 2 circles on it. I'm sorry, it's a NAND with 2 circles on it. So that gives you an AND. So one NOT changes it one way. When you have 2 NOTs, then it changes it back to the original one. And then you can make an OR gate, but it takes three NANDs to do that. And you think, well, okay, if you're building stuff, why do you want to have three different circuits here to make one? Well, it turns out it turns out that it's just cheaper and easier to make circuits that way, using lots and lots of NANDs. Okay, so here's the diagram of what we're going to use. It's we call this a DIP, D-I-P, double inline pins or double inline package. So there's a set of pins, 7 on this side and 7 on this side. And this has 4 separate NAND gates in it. And it has voltage you have to apply here. Okay, all chips need to be powered with 5 volts and ground. Okay, even there are many transistors, several transistors at least, inside any of the gates. So the gates need some voltage to operate on, independent of what voltages you're putting on the inputs here. Okay, so you always have to ground, like pin 7, and put a voltage 5 volts in on pin 14. Then you can use any of these four gates here. And the NAND gate is a 7400. So the 2 zeros say that it's a NAND gate. They also have 7402, 7404, 7408, 7432, and so on. Any questions on that so far? So we'll get into this a little bit more on actually using these. Okay, here's a problem, a digital circuit. Okay, you make a circuit out of these 5 different gates, an OR, 2 ANDs, and 2 NOTs. And so the practice is, the problem is, what does the output look like given just 2 inputs? I mean, you could consider that this whole thing is just one gate, right? 2 inputs and 1 output. Okay, let me go to the next slide. Okay, so the way you work this out is you just work your way through. And let's do this. I would normally do this on the board, on the whiteboard, but it's not that easy from here. So I made all the separate steps here. Okay, so the first thing you do is say, I'm going to put 2 zeros on the inputs, a 0 and a 1 and a 0, or 2 1s on the inputs. And then you just follow it through. You say, okay, if I have a 0 here, it goes into this AND chip as a 0. But the 0 goes through the NOT, so it puts a 1 down here. And likewise, this 0 puts a 0 here to this AND, but it goes through this NOT to give it a 1 here. So this, this AND has a 0 and a 1. But I want you to notice something, a shortcut. If you drew a line through the center of this thing horizontally, one side would be a mirror image of the other. There's symmetry along a center line. So whatever I do to the top half, it's a mirror image on the bottom half. So if you're going to figure something out, you only have to do the top half since it has this symmetry. Okay, so let's continue on. So you have an AND, but you have a 0 and a 1, and that gives a 0 out. And that 0 goes to the OR gate. But you have 2 zeros going into the OR gate, so you're going to get a 0 out. So 0 and 0 are going to give you a 0 out. Okay, if you do 0 and 1, you can go through the same thing. The difference is here that this is a 1 now, so you're going to get a 1 here and a 1 here, and this 1 goes up here to be a 0. So this is the same as basically, well, you're going to get a 0 here because it's an AND. But here you're going to have a 1. Before you had this, now you're going to have a 1. Okay? And then you have a 1 and a 0 in the OR, so then you're going to get a 1 out. Okay? But remember what I said about the symmetry, about the line. See, I've broken, on this one, I've broken the symmetry because I have now a 0 and a 1, so it doesn't have this mirror image anymore. Okay? So whatever happened up here, you don't have the mirror, well, you don't have the same equal mirror image here. It's inverted. Okay? So you can, so now use more symmetry. You can say that it doesn't matter if you flop these two things, if 0 and 1 and you have 1 and 0, you're going to get the same answer out. You're going to get a 1 out. Looks like, so you're going to get a 1 here and a 1 here. And then you can do the final one. If you have 2 1s coming in, you're going to get a 0 out. Okay. You have symmetry here and symmetry here because you have a 1 and a 1, and you also have symmetry of all the parts. You have sort of physical symmetry with the parts, and the 1s also have symmetry, mirror symmetry. Okay, so what you get out of this circuit is an exclusive OR. Exclusive OR. Okay, any questions on how to do this? I'm sure there's going to be something like this on the exam. You just basically follow it through. You have all these intermediate points, and you just write down what you'd get at the intermediate points here and here, and then finally the answer. Any questions on this? So originally I wrote C and D here because those were intermediate points. Okay, so let's do the first 3 minutes of this.
This is a revision video for P6C, combined logic gates and using logic gates.
You might have to turn it up.
When you need a switch to a real-life situation, you usually need a combination of logic gates. One example is when you open a car door. A light usually
Yeah, Professor, could you turn up the audio?
when you open
Hello?
Can you turn up the audio? It's hard to hear.
Let's see.
I think you need to share your computer audio.
Continue to share the audio.
Like when you click on the share screen settings, there should be an option to also share your audio.
Share computer audio. Okay, how about that? Okay, the point of this this short video is that here's something that's actually in use where you're going to use logic to do something, to turn on the light when you open the door in your car.
The driver's door, or the passenger door, or when you press the switch. To show this, you need a combination of logic gates. The two gates in this example are both OR gates. So remember, either input.
Can you hear me okay when I use my voice?
Yeah, the audio is much better now.
Yeah,
And
everything's good.
We can still hear you.
Anyway, instead of her talking, you know, I'll just say that you want to have something that's going to turn on a light when you open a car door. So if you have two doors, you have a driver's door and a passenger door. So you want an OR gate that says if either one of these is open, then turn on the light. But you also want to be able to turn the switch off so the light doesn't come on when you open the doors. And so that would use two OR gates. So you have to have this condition on. Well, okay, I take that back. This D turns a light on independent of whether the doors are open or not. Like if you wanted to read in your car, then you just turn the switch on and you get some voltage out here to turn the light on. But then if either door is open, then you will also want the light to come on. So the three things can turn the light on: opening a door or turning on the switch. Anyway, that's basically all she was talking about. Okay. Okay, we're coming near the end here. So you can do math with these gates. There's something called the half adder and the full adder. Let's go through the half adder first. Okay, so here's the math. Okay, you want to add two numbers in base 10, a 5 and a 3, which is 8 in base 10. So you're going to write 5 in base 2 here and 3 in base 2. So the A represents the least significant figure, and that's a 1 here. And A3 is the most significant digit. That's the 0 here. So then the sum is going to be represented as S0, S1, S2, S3, where this is the least significant digit. Anyway, but we do the math just like we did with the base 10, and we have to have carry. So here's A and B. You're going to add them. So 1 and 1 is 0. Like if you had if you had to carry one, if you had to carry something, if you're adding in base 10, when something is more than, if it's more than 9, you have to carry one to the next position over. So here you have 1 and 1 is 0, but then you carry to 1 over here. So then the carry 1 and the 1 is another 0 and a carry over here. So then you have a 1 and a carry. So that's 0. But then you have a carry over here, and that's this. So this is a number in base 2, and this is a number in base 10. That's just that simple. Okay, you can do this with this. So this is the exclusive OR. Okay. And then if you have a carry, so if both of these are 1, then you know that you want to get a 0 out and a carry. And that's just what this does. So you only get something out here when you have either A or B is 1, but not when they're both 1. So when they're both 1, you're going to get a 0 out here, and you're going to get a carry. Okay, so you have A and B coming in. This is for 1 digit now. For every digit, you have to have an output and a carry. Okay, then you have a full adder. The difference there is you have a carry coming in. So you're going to have 2 exclusive ORs, 2 ANDs, and an OR here. So the difference here is you can have full adder, you have 2 bits coming in and a carry coming in also. You have the sum coming out and the carry coming out. That's a full adder. Okay, so these things are used a whole lot in computers to do almost anything. So this is just for 1 bit, and then for every bit, you're going to have one of these full adders. So if you have a 4-bit digital number, then you have to have 4 of these full adders. Any questions? Okay, so Minecraft. Let's take a look at this. This is a really interesting little piece of software. Logically, you can download a free trial, or you can just try it online. Hold on here. Let me share it. Sure. Okay. So so you can try Logically online. You don't have to install it. So it has switches, it has output, it has various gates, it has flip-flops, which we'll get into later, actually next week. So let's take a switch. You just pull it out here. And if you have a light bulb, you just wire it. So these are the switches like you saw in Minecraft. Down seems to be on. Where, I don't know, most house switches, you flip them up to turn them on, right? But this and Minecraft are the opposite. So when you see, when it's down, you're getting a signal to the light bulb, and the light bulb, even though it's dark inside, shows that the filament is white. Okay, so you can take the XOR gate. You have 2 inputs, so you can have two switches here. Hook up the two switches, see what the output is. That'd be like your LED. So when one of them's on, you get an on, right? When both of them are off, it's off. And when both of them are on, it's off because it's exclusive. To get it on, you need only one of the two, but not both. So you can build up lots of circuits this way, and you'll use this. You can use this for your lab report too. And take a screenshot of it. Okay. Logically. Oops. Okay, so you're going to test logical gates in the experiment this week with 0 and 5 volts. You can use the LED with a current limiting resistor to see when things are on. You measure truth tables of unknown gates to see what the gates are, and we'll go into this Wednesday. But let's take a look at this. This is the last thing here.
Grammarly does more than catch errors. With Grammarly, you can find really good, no, perfect.
In this experiment, we're going to look at integrated circuits, and we're going to build some experiments from the course notes and implement them on our breadboards. We're going to first look at the chips themselves. This is the type of chip that we're going to use, the type of chip packaging we're going to use. It's the DIP packaged chip, which means plastic dual line, the pin package. And the pins are spaced at 3/10 of an inch apart. And you can see that you have a little circle here at the very top that indicates that that's pin 1. So there's a little notch at the very top of the chip, and there's a circle there that indicates that this pin here is pin 1, so that we know how to identify it. We have to be very careful that we order the DIP package chips when we're working in our experiments and so on, and when you're doing your projects later on. There are other packaging types available. This is an SOIC, which is a small outline integrated circuit, and you can see it's of a considerably smaller scale. The inside of the chip might be exactly the same and might do exactly the same function, so just the plastic packaging and the pin layout and so on is what's different in this format. Again, it's got a circle to indicate that pin 1, but you can see it's considerably smaller than the DIP packaged chip. It is possible that the chip that we want to use is only available in a DIP package, and in which case we can use a board like this. It's a converter board. It allows us to packaging format, which means it could also be letters like S, manufacturer, which is Fairchild Semiconductor. It could also be letters like SN, which would refer to Texas Instruments, for example. The 7-4 is the way that you know. I suppose this is the giveaway in terms of finding the number that makes sense on your chip. The 7-4, and you skip the letters in between, 7408 refers to the particular type of chip. This is a quad 2-input AND gate, so there's 4 2-input AND gates in this particular chip. The N at the end refers to the packaging type, so we know that this is a DIP packaging type, so the N refers to DIP, the dual inline packaging type. And finally we have the HCT in the middle, which refers to the particular logic family that the chip belongs to. In this particular case, it's a high-speed CMOS with TTL logic levels. So this is the particular type of chip that we're going to be using for our experiments. The first thing we need to do is we need to connect up the power to the chip. So I've set up the rails so that we have easy access, and this particular chip, pin 7 has to be connected to ground, and pin 14 has to be connected to VCC. So here we're going to connect pin 14 to VCC, and pin 7 to ground. Okay. So our chip is powered. I haven't connected the supply yet, but the chip is powered. And then we have on our input on pins 1, 2 and 3 again, we can tell our first pin by the circle that's just visible there on the top of the chip. We have pin 1, 2, our inputs, and pin 3 as our output. So we need some way of seeing our output, so we're going to use an LED for this. So I'm just going to use an LED on pin 3. Connect the LED, well, this is a piece of wire. I'm going to bring the LED over here, and I'll just use a small resistor tied to ground as before, and then we just bridge that. Again, remembering the longer leg is the positive, is connected to pin 3, and the shorter leg is connected through ground, to ground through the little resistor. So now we have our circuit, and we can test it, and we can say, well, let's connect both of our inputs to be high. And in this particular case, when we turn on the power, you should see very quickly that we get a value of our LED should light. So connect pins 1 and 2, both connect both to ground, both to VCC to 5 volts. And when we turn on our power supply now, you'll see that the LED lights. I'm just going to leave the power supply lit, and I'm going to disconnect one of my inputs and connect it to ground. And there you'll see that now that it's connected to ground, the LED is off. If I do it on the same with the other pins, it'll have the same effect. You'll know from the truth table for an AND gate that both inputs have to be high for the LED to be lit. So if I again set both inputs to be high, then we can light our LED like this.
Okay, so yeah, I just wanted to show you that part there about hooking up the chips. The decoder, we're going to cover that. We'll cover that on Wednesday. Any final questions before we sign off?